What I will cover in the next slides is, first of all, the reasons and a bit of history of what we did in the past 5 to 7 years, the design of HEPscore 23, results from new adopters, and also the future work. Now, oops, okay, now as I delay this. Okay, so all this is about server performance comparison. This I want to highlight. So we really, with the benchmark, compare the performance of the servers more than the profiling of the application. So, and this I want to make clear, given the majority of the subject in the computer and accelerator forum. And what we believe we have found is a right measure for the estimation of this performance. But what we do is comparison of machines. And this is what AI thinks in terms of comparing 2 different kind of vehicles moving on the certain genes. And by the way, this will be the only AI thing that I will show today. So let's move on. So WLCG, I don't have to explain here, but let's consider those under 70 sites or more that serve for the scientific purpose of the LHC computing grid. So we have 1.4 million of CPU cores that have been deployed through decades. This means that we don't have the same CPU model, we don't have the same kind of memory, motherboards, we don't have even the same configuration, so things in terms of frequency settings, covariance, and so forth. So all this affects the performance of cores. So what we need when we compare, we count the number of cores that we have, we need to normalize them by an effective performance. And this is where benchmark scales enter in the game. That is also, it became recognized as a currency for many of our evaluation of the resources. I added here a plot that was produced by Andrea Chavar a few days ago that shows you the current status of, let's say, the CPU models that today serve the CMS jobs running in the last month. So as you can see, today we have a sort of dominance of AMD, ROM, Milan, but then what follows are Intel models as well broad, well up there, and then more modern models that are emerging, like others, we see Naples, Genoa. So we have to take into account all those aspects when we have to, for instance, follow the accounting reports of sites, consider the set pledges and compare them. We do this once a year. When we consider the experiment predictions, and here we have an example from Atlas. I will see it. So an example from Atlas that is well known in this community. So this represents the 2 scenarios of computing needs of Atlas with conservative or aggressive R&D along more than a decade of activity. What is interesting is that here, as you can see, the scale is normalized to a benchmark. And the reason is that, okay, you know the complexity of events, for instance, in round 4, WLCG, based on the number of events of pileup, you forecast the complexity of the single event processing, then you calculate the number of events you need. But at the end, to then normalize this to something that is comparable with the current course deployed, what you do is that you normalize by the benchmark. That has been until last year, HEPscore 6, as you may know. So similar things you see here. So this affects also procurement, because clearly sites that have to purchase new hardware, they will put in the reference of their technical specifications requirements like this CPU has to deliver at least that amount of benchmark scores. So I already mentioned HEPscore 6. This has been the benchmark that our community has used since 2009. Before we had SpecInt, and that was another industrial standard coming from the spec organization. And even earlier, we had in-house benchmarks like the CPU unit in the early 90s. At that time, were workloads from at the time experiments running a simulation and a reconstruction jobs. So you will see this as reflected to what we have today. Anyway, for what concerns HEPscore 6, this is a table that just reminds what it contains. It contains 7 workloads. 4 of them are dominated by floating point operation, the other by integer operation. They have nothing to do with the events-based reconstruction that we have in high energy physics. Some of them, yes, have to do with physics, but others not. So for instance, here we have an XML parser. Others are simulation of very complex proteins, but nothing to do with what we have. Nevertheless, at the time when it was introduced in 2009, it proved to be highly correlated with the workloads that at the time were used in our community. I like a lot this bottom table because this comes from the paper that essentially introduced in 2009. So it was presented at CHEP 2010. HEPscore 6, and as you can see, so this was the set of machines on which it was used to benchmark. So those were essentially machines with a single core, 2 times single cores, or dual core, maximum 4 cores. So what we have is that today this kind of benchmark on our machines runs on around 3 hours. But then since 2018, we learned that HEPscore 6, or better, spec CPU 2006, on which HEPscore 6 was based, was not supported anymore by the spec organization, that on the contrary suggested to adopt a new benchmark that is called the spec CPU 2017. If you have questions and you want to ask now, probably we can even stop. If this is more open conversation, then if this can help in clarifying things, good.
No, I'm just amused by the typo. If it is coming one-to-one from the paper, there's a typo in the very last line.
Yeah.
Harper. Yeah.
Okay. This is coming from that paper.
Okay.
Yeah.
Yeah, then I was just amused that there is a typo in the name of the processor.
Okay, so starting from 2018, also triggered by this need of evaluating a new benchmark, we started a number of considerations, considering if we had to then move to spec CPU 2017 or consider a benchmark based on the app-specific workloads, so what then became HEPscore 23. There were many motivations to consider this. One of them is that doing profiling studies based on performance counters, we could see that for instance, the amount of time spent by our application in the front end or the back end or in the best speculation of the processor was completely different with respect to what we had in the different spec benchmark. And that plot that goes back to 2019 shows this in, let's say, a dendrogram of similarity, where essentially branches that are nearby means that they tend to be similar in terms of the utilization of the CPU. And what we could see is that clearly, so all the workloads of the experiment, or at least the majority, they were sitting close in this space of utilization of the CPU, when on the contrary, all the workloads coming from spec, whatever they were from 2017 or 2016, they were far away from that. So this was another motivation that then we wanted also to have a benchmark that had been open source, that we could expand to GPUs in the same manner as they've introduced a new one for GPUs. So the reason why we started really to consider if, from the technical point of view, this was feasible. And this is when we started then to propose HEPscore. So the proposal came around 2017 in Manchester, but has been a long process to arrive to today. So we had, first of all, to prepare a prototype, gather the different workloads from the experiments, also increase consensus in our community that clearly was for essentially 10 years used to another benchmark, to another approach, in which essentially you don't have to care about building your benchmark, but just taking the what comes from industry, from a distributed tarball at the end. I think the point in which we convinced the community was with the publication of this paper, when with what we call a HEPscore beta, we proved that we could use a combination of workloads of the experiments to benchmark machines. We proved that those measurements would have been robust. They could resolve better than HEPscore the performance of machines, and also we could do that including workloads of multiple experiments. They were workloads from run 2 at the time, plus the workloads from bell 2. So this moved us to go forward. We got the green light to consider workloads from the run 3 of the LHC experiments, plus evaluating other workloads from other experiments like Juno and gravitational waves. So this brought us to the creation of HEPscore 23 in 2022, with the delivery in 23. The most difficult part, let's say, of 2022 was the definition of a transition from the old unit, HEPscore 6, to the new one. How to make sure that this would have been a smooth transition and not, on the contrary, a breaking step that would affect pledges, would affect accounting, would affect a number of phases, including procurement. So the crucial date is April 1st, when starts the new year of pledging and accounting, and then it was agreed by the management board meeting that HEPscore will have replaced the HEPscore 6 on that day, starting from that day. What is HEPscore? How do we define it? I will spend a couple of slides on that. So the functional definition is similar to HEPscore 6. So there are mainly 3 components. We get a set of reference workloads. Then you have a machine on which you will execute this. This is the reference machine. And what you do is what is summarized in this table. So for a given workload, you measure the performance in terms of a speed factor. So for us, it's the event throughput on the reference machine, as well as in other machine for which you want to define this new score benchmark. Then you rescale it to the reference machine. So the reference machine has by definition a value of 1 for each of those workloads, and the other have a factor with respect to that. Those factors, given that we use more than one workload, are averaged, but not with a standard arithmetic average, but with a geometric mean. What is the advantage? Being a ratio, the advantage is that the geometric mean, by definition, preserves its definition when you do the ratio. So that if you do the ratio of the score measured with respect to the reference machine of a server A and respect to the same score for server B, you have another score, this time referred to the server B. And this is an advantage because this allows us to, if you want, even to redefine the reference machine without breaking the way to compare the different servers and generation in the future. And again, this is what also HEPscore 6 implemented. The workloads. This is a a question that I get often, so I describe really well what we mean as configuration of the workload. So given a workload, let's say Atlas simulation workload, that is a multi-threaded workload, what happens is that typically the application is configured to run on any given number of threads. Typically on grid jobs is 8 threads. In our case, we selected 4 for a simple reason that it's easier to divide by 4 the majority of the servers. We could have servers with 12 cores, for instance, or multiple threads. So this makes easier the splitting. We want to saturate the machine. So when we run the workload, the machine has to be fully saturated. This means that if we have an application that runs on 4 threads, we have to run in parallel multiple copies of this application. And this is what I represent here with this shade of rectangle, blue rectangle, where you see multiple copies of the same workload. Each copy runs from core 1, let's say, to core NT, where NT is 4. There is an exception for that. That is when we have workloads that are a single process, and we have them. We have them because experiments still have them. So in that case, clearly, each copy corresponds to, so essentially will correspond to a core. Apart the splitting in this way, we don't pin cores. So this has to be important to be understood. So we don't pin cores. This means just that the number of threads that we run or processes or copies has to be equal to the number of available cores to saturate it. After.
So out of curiosity, in this case, when we're dealing with copies of processes, are these processes doing exactly the same? So are they are running on exactly the same input data?
Yeah, they run on the same input data. They follow, so we also impose the random seed in the copy, so that essentially we can follow the same sequence. There is some randomness because in multi-threading, experiments don't arrive to guarantee that really, let's say, the second event will run on a specific core. But yes, so the copies have access to the same input data that typically they split the copy or will link, it depends the configuration. And yeah, we do that. So we want a reproducibility because then, for instance, we run 3 times. So we run always the same workload in all servers to compare them, but also we run 3 times each workload. The reason why you see those modularity of 3 for the 3 example workloads that I have there. The reason is that then we take the median of the 3 execution as a representative score for that specific workload. So what we get is now a sequence of n scores, and as I mentioned in the previous slide, we do the geometric mean of those scores that are event throughput referred to the reference machine. Okay, so this can be done, but what was the real challenge? The real challenge was to collect the workloads of the experiments. So each experiment has its own framework, has its own way to distribute the software, distribute the condition data that are the most difficult part, because software and input data perhaps are easy to get. You know, you get a root file typically and it's done. Condition data are not so trivial. We wanted to do that for multiple experiments and also multiple times. So for different workloads, simulation or reconstruction, following what the experiment do in production. So there are experiments that run GenSim together. There are experiments that, on the contrary, do generation separate from simulation. Others that do GenSim Rico in a train sequence. So we mimic that, and this is contained in the workload. How to do that? So, and how to do that in such a way that every user can run without remote access, without access to the database, using more or less a similar interface. So having a common way to retrieve data and then display them. So all this was what we needed to do. And one of the enabling technology was the containerization. So we could create containers that would do all this as it was for some user to run a script, let's say on LX Plus sourcing CVMFS. So everything is in the container. And we started with Docker, then we moved to Aptainer. So Docker is still, as you will see, what we use to build the containers. And on the contrary, Aptainer is what is used when we run the benchmark for the performance measurements. So again, what we have in those containers? Somehow we have to write an orchestrator that is able to read a configuration file, access, source the experiment environment, like it was on CVMFS, but in this case is on a snapshot of CVMFS that is local to the container, as to access input data, as then execute the processing, and then parse the results to then produce this output. All this would not have been possible without the synergy, the common work between two classes of experts. From the experiment, we had the expert that provided the software, data, how to parse the results, how to also solve discrepancy that we discovered. From the benchmarking team, we had the expert that implemented this unified approach, the building, the validation steps. And here is, I try to give you an idea of the steps to build. So we build containers based on GitLab CI infrastructure. As I mentioned, we run there using Docker container. So we start from a container that mounts the CVMFS, and then we profit of a second enabling technology, that is the fact that we can export from CVMFS only the software that is needed, that was needed by the application. So this is what happens in this chain that you see here, that from 1 to 4 essentially runs a first run of the application that allows to access CVMFS, execute the application, then snapshot CVMFS, copy that snapshot inside the container, and then validate it. And this is done for multiple architectures today. So we have a build for ARM, we have build for x86. We are currently also building for x86 plus GPUs. We still don't have cases of application that can run on ARM plus GPU, but as soon as we will have, and as soon as we will have also machines, we will be able to build them. Okay, so in terms of project, if you are interested to the code, so our project is structured in three different packages. One is HEPscore, that is essentially a Python code that is used to do what I just described, so orchestrating the execution of the experiment workload and then creating the final score. The HEP workloads, that is where we build the individual containers for each experiment application. And then also we have what we call the HEP benchmark suite, that is on the contrary okay, so let me finish this and then I will. So this slide. So the benchmark suite is an orchestrator of multiple benchmarks that we have used to need to collect results from many sites, not only at CERN, but remote sites. And as you will see, it's really pivotal for a common database of benchmark results. So you have a question, but I don't see it.
Yeah, Andrea, do you want to go ahead?
Hi, everybody. Hi, Domenico. This is Andrea from CMS.
Ciao.
I just wanted to comment on your previous slide. The CMS GPU workflow that you have should actually be able to run on ARM plus GPU.
Okay.
If it doesn't, I'm happy to provide you something that does.
Okay, good. Good to know. Okay. So we will soon update this picture. Thank you, Andrea. Okay, So I have to make here a clarification. I have to precise that we use the term HEPscore to identify two things. The code that orchestrates multiple runs and then multiple workloads, and then performs also the final evaluation of the score, and a specific configuration. That configuration is called HEPscore 23. That has then a frozen set of workloads with a frozen set of input parameters. So when I mention HEPscore 23 is the benchmark with that specific configuration. When I mention HEPscore is the package that implements that benchmark. So HEPscore 23 will not change in terms of, let's say, configuration, but we could have new version of HEPscore as the package. And indeed, we are preparing a new one, a version 2, that adds a new feature that were requested after that we delivered the version 1.5. For instance, there are ways to configure the number of cores to run easily a thread scan. Or there is a simple way to define the configuration that you want to run. If you want to run from Docker, you want to run from CVMFS unpacked images, you want to run from Singularity, because we offer the three way to access the workload images. But again, this has not impact on the score computation. Okay, so now the workloads. The selection of the workload for HEPscore was work done by essentially two teams. If all the implementation or the design, all this activity was done mainly by the HEPiX Benchmarking Working Group that still continue to do this work and maintain the infrastructure. On the contrary, the selection of the workloads was considered by the WLCG Management Board a task that would need a dedicated task force for that. So a task force was created with a representative from sites and from the experiments. And that task force, as you can see, worked for more than 2 years to then identify the composition of the HEPscore 23, and in particular to identify the strategy for this transition from HEPspeco 6 to the HEPscore. And here I mentioned the people involved in both activities. Okay, so what we did to then identify the set of workloads. First of all, given the 11 workloads that we got from the LSC experiment, BEL2 and Juno and gravitational waves, what we did was to validate each individual workload. So here you can see that we did run on, so it's visible, yes, more or less. So for essentially 1 year, we ran multiple configuration on 46 different CPU models offered by 15 sites. And what we did was to measure the reproducibility of each workload, its stability, so no crashes, no failures as much as possible. The resolution that, as you can see here from those plots, was typically very good, so less than 1%. And also the duration of those workloads. It was also an occasion to then offer those workloads that are in containers to experts of performance analysis. And this opened also a way to investigate features of our workloads from experts that are not part of a specific experiment, let's say, that could look also in other experiments. In that case, for instance, at the HEPiX workshop in September 22, Vincenzo gave an extremely interesting talk analyzing a number of aspects of those workloads, doing perf analysis or studying the resource utilization, and discovering also interesting things. For instance, he identified a peculiar hotspot in the LSCB simulation that was essentially connected to the way to navigate giant surfaces that just fixed, so in a really small amount of lines that Andrea here present that took care of fixing the LSCB software, gave a speed up factor of 2 in LSCB. So we are not talking here about peanuts, but just this change provided at that time an important improvement in without changing at all the physics results, because this was about the jump for navigation.
I think it's all properly.
Just out of curiosity, does this mean that the containers came with debug symbols? Or how did the containers help in drilling this much down into the code?
I don't know if Vincenzo is connected here, but he could use Singularity and run. Vincenzo.
No, I run on Metal. This is completely on Metal, because you can just run the HEPspec on Metal. And then once they run, you go inside the directory, you navigate, you push them, and then you run.
No, but
So we were running on Metal because that's where the machine that the HEPiX working group provide me, and actually many tests are done on Metal, not on the container.
And you were accessing Singularity, but I think the question is about symbols.
At least to perform, wait a second, at least to perform the sum of the perf part. Others can be done on the container because you can use perf outside the container. If you have root privileges, then you do perf must. Because you run on the full machine, you do perf stat -a, and then essentially you perform performance measurement on the whole machine, and that's independent of what is running, and it will report. It's actually is much more. It's more supported than user mode. I mean root usage of perf.
I maintain my question though, that is it really realistic that as long as the experiments provide a containerized workload, that you would ever be able to drill down into lines of code without extra knowledge about how HCB software works, how to compile HCB?
Yeah.
I mean, this is an activity that we do with external software all the time, including root and TensorFlow and things like that, because we discover things that we don't understand and we have to dig out where the issue are. So that's something that 20 or 30 years I'm doing regularly. Actually, it's my job in CMS. It's my main job in CMS.
Vincenzo, it's Andrea.
Don't do that, you don't control your software, or you write each single line of code.
Vincenzo, it's Andrea. It's just to say that what you did was to, I mean, with perf, it was enough to have the profiling of where the time was spent, and then actually going into the lines of code inside that continuous, then externally. But already to know, I mean, what Vincenzo did here was to actually find which routine was spending the time, and this you can do with the container. Then actually he went and looked at what this routine was doing outside. But, so this is enough.
Okay. No, if the claim is that at least a function name can be reasonably figured out. Okay.
Okay, let's move on. So we had to select then the set of those 11 workloads to be used for the definition of HEPscore. And we had a number of choices. So use all the 11 workloads, exclude some that will run for a very long time. So look at subsets, and then even with subset, we had two options: to use weights or equally weight all the workloads, with the effect that weighting would have been proportional to what we consider, for instance, weighting based on the grid fraction of jobs. But this is something that then included another terms of negotiation, no? So what used on that? What was interesting is that we tried a number of those things, and at the end we saw that in terms of scaling factor from a CPU to another, the change was small. So here you see numbered up to 38 multiple CPUs, and you see different candidates HEPscore. So given the small difference, so we had a preference for a small set of workloads that will make shorter also the runtime, to include the Alice reconstruction of letless events, that is a completely different approach, as also a different paradigm for the way to reconstruct, because there is this concept of the time frame with respect to the event-based reconstruction, and use the simplest approach of unweighted workloads that simplified a lot the selection of the parameters. So in this way that then we came out with the HEPscore 23 that contains those 7 workloads. From Alice, we take DigiRico. From Atlas, the generation based on Sherpa, that is a single process application. Reconstruction, that is multi-threaded. Bel2, that has GenSim Rico in a single train, again, single process. From CMS, we got GenSim and Rico, and from LCB, simulation. With, as you can see, a sort of balance between different kind of multi-threader, single process applications, Rico respect to simulation. The versions of the software were essentially the most recent one at the time when we froze the configuration, and we could produce workloads, so containers that supported both x86 and ARM at that time, so 1 year ago. And that was also another achievement, big achievement, because at the time, not all the experiments had production software running on ARM. Some of them had a plan to do in the future, others had no need, like Bel2, but there was an effort to, in any case, migrate this code to ARM and make sure that we could use this new benchmark, not only for x86, but also on ARM. And that has been a crucial aspect because, as you will see, so it's being used a lot in to benchmark ARM nodes and also compare things like performance versus energy consumption. So to give you an idea of what is perceived from the monitoring point of view of the server utilization metrics, here I show what is the system load, the CPU usage, and the memory usage for the reference machine that I remind you is an Intel Gold with 64 cores when it is in SMT on. And here you can see the 3 runs of Atlas Gen, SIM, CMS Gen SIM, CMS Rico, and then LCB, and then Bel2, and then Alice. With the CPU usage that is saturated, with memory that is in any case less than the maximum memory available, let's say that is 64 times 2. Apart some sporadic peaks that we have seen, I will detail this later. If you notice the difference for the Alice workload, in particular in terms of load, this is due to the specific way that the software of Alice essentially deploys microservices. So these microservices are there alive. So this implies that in the processor queue appears as alive processes, then this increases the system loads. But those are essentially services that are waiting to act, and then there is a messaging system that essentially dispatches results, that means events to process. This has an implication that essentially you see here, but is well known and completely acceptable. Other things that we could do is, for instance, a thread scan, as I mentioned. So HEPscore 23 by default saturates the machines, but we can do something that is interesting when people do studies, like changing the number of copies and then do a thread scan. Here I was doing a thread scan from the minimal granularity of 4, then 8, 12, and so on and so forth, up to the saturation of the machine. Was what to move from HEPscore 6 to HEPscore 23 to this configuration? I think that the top plot shows this. In this plot, we report the ratio of the score measured with the HEPscore 23 with respect to HEPscore 6 for different CPU models, and the x-axis represents the year of delivery of this CPU model. So more recent CPUs are on the right, and then older CPUs are on the left. What you can see is that this ratio is clearly normalized to 1 for the reference machine. That is the machine for which we have, let's say, normalized the score HEPscore 23 to HEPscore 6 in order to make smooth the transition. So what you see is that when we go back into the past, this discrepancy increases. So this means again that you can see this in two ways. So you can see in this way and say, okay, there is a deficit for all machines, or you could say in the other way that with respect to the expectation done in 2012, today our workloads deliver more than what HEPscore 6 will say for a given specific hardware. Okay, so I think that this is the plot that confirms that our bet there and our motivation was indeed is reasonably good. Also in terms of resolution, we have a pretty nice reproducibility. So again, less than the %. And the running time on the current machines is around 4 hours. So a little bit more than the 3 hours of HEPscore 6. Other things that tells us that was a good choice is this study in which we essentially studied the correlation of the benchmark that we had in hands, so SPEC 2017 HEPscore 6 and HEPscore versus the workloads that came from the experiments. And this figure of merit is a metric that tells us, let's say, how good is the linear fit. So smaller is better. And we get a systematic better performance for HEPscore 23. I think that even more interesting is the fact that as I mentioned in the diagram that shows the similarity, our application tend to be similar in the way they use the CPU. And this is reflected by the fact that if we remove from the definition of HEPscore 23 a single workload, and we rerun to then again evaluate the performance of different CPU models, what we get as discrepancy is something that comes in the percentage level. This you can see from this plot, in which essentially the x-axis numbers CPU models, and on those CPU models, what we did was to measure the HEPscore 23 and then the redefined HEPscore 23 without a given workloads. So the different symbols are what we remove from the standard definition. And the bottom plot is the discrepancy in terms of variation. And as you can see, this ratio is within a few %. So again, few % of discrepancy, even if we have to, let's say that we drop a workload, or it's extremely reasonable in terms of what is the accuracy that, on the contrary, we need for the use case of a benchmark. A quick overview of the documentation, if people still don't know, so let me advertise this. In the HEPiX website, there is a benchmarking page that details how to install and run HEPscore 23, how to contact us in case of needs of support with a GCAS ticket. There are results about the HEPscore 23 scores on servers that have been benchmarked. I will come later on that. You will still find the legacy pages of HEPscore 6, and you will find also instruction for the accounting reports. That is, in any case, a task of the accounting task force, and they will not cover here. But I will cover what we did to transition from HEPscore 6 to HEPscore 23. So first of all, the easy thing to do is to make smoother this transition, normalizing for a specific machine, the reference machine, the two values of HEPscore 23 and HEPscore 6. And this is what we have done. Second thing that is more a political approach was that was decided by the management board that the capacity deployed before 2023 will not need to be re-benchmarked to report the value in HEPscore. So HEPscore 6 score is still valid. And this goes back, if you want, to that plot. So sites that will re-benchmark will get a penalty if they have all the resources. And then we don't want to push for that, as I say. So they are clearly encouraged to buy new resources when it will be possible for them. But we don't want to penalize them. So this was the decision. All this information has to go then for the new deployed capacity in the accounting portals that are Apple, GI Portal, wow. I think that you could be interested to look into the page that exposes the results of HEPscore, the public results. We collect them in a database, and then this is an open search database at CERN. Many people have access. If people are interested to do specific studies, can have access on that. But we consider it easier to expose the results through a static table that we update every time there is a new entry in the database. This table essentially is in the HEPiX repository, GitHub repository, and then gets translated immediately on the HEPiX website. So if you go to the link, you will see really what was available. It's available as official benchmarks done until the last 24 hours. And those are some results. I hope that you can see them. I see them at this distance. On the slide will be clearly easier. So here, for instance, I put just the top 10 CPUs, but we have in this table 110 distinct configurations coming from more than 20 sites. What is interesting is that we have an order of 10 ARM-based servers. We have Neoverse and one, so Ultra Max. We start to see some Neoverse V2, so better known as Grace. You will notice that if we sort them by what is the you don't see it, so because there is this
hide that. So you click more.
Where more
and then hide meeting controls.
One
that's Control Alt Shift page.
Where do you see it?
One more down.
Okay, yeah, nice. So if we order them by score, and we get to the top 10, you see that most of them are dominated by AMD, and we start to see the Neoverse. In the top 10, the Intel one that we have is this Sapphire Rapid here. Again, this is modulo the number of online CPUs, clearly. So it's not just the delivered performance per single core. But keep in mind that the rule of thumb of 12 HEPscore 6 per core that we used in the past is gone now. So we have for hyper-threaded machines easily 15, 17 HEPscore per core. When we go to the not hyper-threaded one, we can easily see even 30 as a number per core. So very, very large numbers there. Okay, so this I mentioned. So we have a database that allows to collect those results. It's easy to send the results. This is what the suite has been considered for. So we invite really sites that want to run HEPscore, not just to run the application that is easy because you install with pip HEPscore and you run it, but we provide in the documentation that I mentioned a script that installs also the suite and easily enable the fact that we collect the results done on the site, and then again they are available for the whole community. that I think is a very important aspect. And this was also mentioned by a number of people. So this is a set of feedback that we got during the workshop in 2022, in which essentially a number of site managers were mentioning if it was easy or not to run HEPscore and the suite. And yeah, so there are messages like how it's useful to get those data published and accessible, the fact that HEPscore allows to compare x86 and ARM, so having containers was a good achievement, and so forth. So nevertheless, we have seen issues. So after that, we started we gave this to the community. So we have seen that in case of a very high number of cores, server with a very high number of cores, we could see failures in the Alice workload to the memory utilization. There is a spike at the beginning of this workload that sometimes saturates the machine. So if there is not swap, some sites don't have swap configured, so the workload can fail. So the workaround is to add swap, but we know the reason and we will fix soon this Alice workload, removing this aspect. We have seen also sporadic failures of the Atlas workload that is under investigation, but it's cured by the fact that we run the workload more than once. Indeed, we run 3 times, but we allow for a repetition in case of failure. So this mitigates the problem. Sometimes we have seen also, we have noticed that SE Linux causes problem to obtainer. So disabling SE Linux is another way to avoid failures like the one that you see here, that in particular happens with obtainers, not with Docker. And another aspect is for CentOS 7, so on very large core counts, ulimits needs to be unlimited. Otherwise, there are failures also there. So there are some tricks here and there that we collect in the troubleshooting area of the documentation.
Sorry, the whole CDMFS thing, I have to ask about it.
Yeah, sure, yes.
So we've been seeing problems with using CDMFS from many cores since years. What is this CDMFS and files saying?
This fixes this issue in most recent. Indeed, this is what we saw in essentially 1 year ago. I know that a new version of CVMFS allows through this CMFS and files to configure the maximum number of open files on the site. So there is this way to essentially increase the number of files that can be opened. In the case of the benchmark that runs, again, imagine that we use not the image downloaded from a GitLab registry like a CF image, but we use the unpacked image on CVMFS. So we will have 500 copies, no? Because single process Atlas will run 500 copies that want to access those files and write and read on those files. This will cause this failure. But again, so this is mainly how to configure CVMFS.
This is an actual failure, so not just performance penalty.
No, exactly. It's a configuration on the site.
Unfortunately, probably not a fixed issue.
That in any case, we don't suggest to use CVMFS for the benchmark. This is mainly used when we run, I will show later, in job. Sites that have to qualify their server should download the CF images. So if you want the standalone tarball and run it. So this is the procedure and this is the way HEPscore is configured to run.
There's a comment from Liz as well. Please go ahead, Liz.
It's just a question. You say for point 1 that you understood the reason and it'll be fixed soon. I was wondering if the reason is on Alice's side, they have to change something about their application, or is it on your side where you have to change the way it's run?
It's the number of events that we configured that is on our side. They don't change the application. The detail is that the concept of time frame that they have, let's say, allows a reasonable number of events in the same time frame. and let's say by mistake we configured a larger number. That was good in our validations until when we discovered on very large machines that this has the implication of this spike of memory, that is when you have to load many events in memory. So it's something that we will cure on our side.
Okay, thanks.
But with the help of the Alice expert. Okay, so we are running late, so I have a few slides. So I want to give you now a couple of examples of how HEPscore has been used after the adoption. So one was clearly scoring the different CPU models that can help driving also decision in the acquisition. But now let me cover three other things. So measuring performance effect when, for instance, microcodes changes are applied, studying power consumption, and also studying the performance of grid job slots. So those are the three studies that I want to report here as an example. So probably some of you remember the vulnerability of last year, down 4, no? And how it was mentioned that it was extremely critical, so covers a number of interprocessor generation from Skylake to the most recent Tiger Lake. And the fact that it's really serious in terms of the way this malicious attack can infer data from memory. The mitigation was a microcode update, easy to apply, but at the same time, so in the few days, even less, that this vulnerability was published, and also the microcode, so were circulated also performance measurement based on other benchmarks, mentioning up to 50% of performance penalty. That was quite scary also in our community, so where people think in terms of what would have been the effect. So we had HEPscore ready, we had the infrastructure ready at CERN to run. So let's say in less than 24 hours, we could collect enough data on the machines that had the microcode update, that are the machine in yellow here reported. So, and for all of them, even if they are just 4, what we could see is that the change was essentially irrelevant, so less than 1%. In some cases, we could even see that the microcode update and the reboot tool there gave us a 1% increase. That clearly is not important because, again, as I said, so there is a resolution in the measurement. So, but the thing is that with this benchmark, we can at least say our workloads will be not affected, and not just fear that, okay, industrial standard like spec is affected or not, but okay, let's trust that this reflects to our workloads. Other thing. So this is something that we discuss often since a couple of years. That is the studies of the energy consumption versus performance is the hot topic, no? So here it reports 2 slides coming both from the HEPiX, the last HEPiX forum, where again, well, I wanted to highlight HEPscore, so clearly I selected the slide that mentioned that. But look from this, for instance, from David, was reporting here the performance of multiple servers at multiple sites. So comparing the R node, so the Ultra and the Ultra Max, with a single socket, dual socket, and comparing also the performance in HEPscore and in HEPscore per watt. So this is what we have enabled with this work. At the same time, we have noticed that now people don't run just the benchmark, but then have to measure other metrics, so energy consumption, but also load, CPU frequency. It's becoming more interesting not just to get a number, but really study the configuration and performance of the server as a whole. So reason why we started a development of an extension of the suite, which easily we can configure plugins that run alongside the benchmark and collect utilization metric from the server. So essentially, they execute standard tools like could be a CPU power call, or could be just an uptime to get load, or a free to get the memory utilization. But this is done during the execution of the benchmark, and is collected as a time series that then we store in our JSON report. We store as the time series that then we can use for in-depth analysis, but also as statistics that then can be used for easy visualization of statistics and studies. So what is useful here is that all this enters in the database, so it is available for everybody, and can be then scrutinized not only by the person that took data, but also by a larger community that could be interested. So I'm thinking at teams, students, so a lot of analysis can be done there. Similarly, so connected to the ability of using those plugins is this other study. So we know that CPU models from different grid sites, even if are the same CPU models, they perform differently. This is a fact we have seen a number of times. This plot that Natalia, our fellow, showed at the Atlas Week, Computing Week of June 2023 is an iconic view of that. So those are sites that have the same CPU model, and this was the performance of HEPscore per core measured on those sites. So it's a bar plot because essentially you see the spread that could be seen in some sites. Other sites are quite narrow, but what is interesting is that they range from the bare minimum per core, that is what we will measure in the most pessimistic scenario with hyperthreading enabled, so that is 12, to the score when bare metal node is with hyperthreading disabled, so that is 22, and they range quite well in this area. But as you can see, different sites have different performance. Okay, how we did that? We were able to essentially inject in the pilot job as a standard job a script that would run HEPscore and would then send to our database those results. So that plot was an evidence, but at the same time open question. Why this? It's for this reason that we continue the study. In that case, we used the load measurement to get an additional feedback. I will show this in the next slide. Let me just summarize here the fact that essentially through the workload management system of Atlas and the LCB, we have been able to submit the benchmark suite and then HEPscore, and we have collected a very large number of data. In particular, Atlas has now this in Hammer Cloud. This means that in order of 8 months, they have collected something like 200,000 jobs results on 8 cores job slots. They have enough statistics to do really detailed studies. And a kind of detailed study that was done is this one, in which the HEPscore per core that you have seen ranging from, let's say, 12 to 24, in this plot is shown as a function of the load of the machine. And what is nice to see is this trend. So essentially, what we can justify as why we see this difference in performance is mainly that servers with different load, so with jobs that are loading differently or job slots that are more or less idle, cause indeed a different perceived performance of the running benchmark. It's quite trivial when one says that in this way. Was less trivial to show this. This is the main trend, but then you can see here also an anomaly, so that diverge a lot from the main trend. And this was a misconfigured site that then we could spot just by the fact that this was a cluster separate to the rest. And in fact, we contacted the sites, and then this was cured, and now clearly the updated plot has those data on the main trend. Here I report another CPU model to give you an idea of that. And also I report an ARM node, on which on the contrary we don't see this sort of trend. So clearly, the fact that we use hyperthreading in x86 has an impact there. In particular, when we are in the range from, let's say, 0.7 to more than 2 of load per of the server.
So did I understand correctly that, so in these cases, the measurement jobs would take, let's say, 8 cores or 8 threads from a CPU that was also doing other stuff?
Yes, yeah, exactly.
So the load is based on other else running generation.
Exactly. This is, in this picture, this is the server, let's say, and we land on a job slot of 8 cores. And then we run 2 copies of HEPscore because we want to saturate the job slots. And the other job slots, we don't know what they are running.
Okay. Then, I am a little bit surprised by the ARM result, because I can come up with a lot of explanations of why what other cores are doing can affect ARM cores. I'm very surprised that on ARM, caching issues don't come up based on what the other cores are doing.
So ARM, this is the first set of data, so they come from Glasgow INFN. Already the fact that it's the same model. Already the fact that come from 2 sites is a good hint that something systematic is there. What I see already is that the frequency of those cores is extremely stable with respect to what I've seen in x86, on which the governor and the way to load balance the load, there is a lot done on the x86 by the kernel on the x86 processor, in particular with SMT on. There are really multiple, let's say, the parameter space of the optimization is large. So there is load, there is the frequency set by the governor, then there is the cache. So there are multiple aspects that needs investigation. What I wanted to report here is just an evidence. Could change or not. I don't have the explanation for ARM, apart that what I've seen is a pretty stable frequency there. There is a comment.
Yeah, I mean, my interpretation for the machine running hyperthreading is that simply the other slots are empty or idle. So as I would expect naively, the HEPscore goes from a factor 1 to a factor 0.5 or from a factor 1 to factor 2, depending on your normalization. Because your normalization is with hyperthreading, it goes from a factor 1 if the machine is full to a factor 2 if the machine is empty and you are running only in 1 slot. And that's rather trivial. So most probably this is not the case, but this is my trivial interpretation of what you have discussed. Of course, ARM does not have hyperthreading, and therefore the slots are not affected by the other jobs. Something else to note is that while older machine were essentially SMP, and including for what concern level 3 caches, a newer machine, including ARM, tend to have large L2 and small L3, and therefore the single CPU tends to be rather independent from the load on the memory system. That's my interpretation of the results.
Yeah, so Vincenzo, you are right on the aspect of hyperthreading enable and less loaded servers. At the same time, what we see that is interesting is the fact that when you go below 1, that is essentially the threshold of just less physical cores used, then one would expect seeing there a flat performance. On the contrary, there are cases in which this increases. And we have hinted that this could be related to still the governor, because if you have a still lower load, then the governor can decide to increase
then you go in, then essentially the frequency is higher than the machine. Sure. But that's, that's a known effect. I mean, if you run a single CPU, this may go to 4 gigahertz. If you run, and also depends on how they are distributed and pinned. So if if slots are pinned, then you would see less an effect. If slots are not pinned and are distributed on both nodes, on both sockets, then the effect of the, say, of the frequency, which, by the way, is not really the pure governor, because the governor cannot do much, is more the throttling, which is internal to the socket itself, to limit the power consumption. So essentially, these are machines which are power limited or heat limited in some cases. And this is why you can also see difference between site and site, because really could depend also on the way the
as we configure
machine are essentially cooled.
Yeah. Okay, so let's move to the last few slides. So future work. Well, I don't have to introduce to this community the activity on the heterogeneous resources and GPU. You know that better than me. So our intent is to prepare also workloads that can run on heterogeneous resources, in particular GPUs. So we have already workloads that run in this way. So Andrea was mentioning before the CMS HLT-like, what we call HLT-like, that runs on x86 and GPUs, and now we run also on ARM and GPUs. We have MedGraph for GPU. We have also a machine learning party flow that is a under development model for training machine learning to be used for the particle flow. Clearly, others can come, so when the community will be ready for that. We are ready to include them in our catalog of containers, because as I've mentioned, what we need is the ability to execute them as if we were on LX+. If this is possible, then we will be able to containerize them. Said that, this is just the start of the investigation in terms of what is the performance of a CPU plus GPU server, because this is a completely new dimension. It's not just saying we have more cores. So how the server has to be saturated now, should be saturated or not, how many copies should run on the GPU to make sure that the GPU is not underutilized, or shall we just run saturated the CPU part? So all those details have to be sorted out. So just the event per second that are delivered, in my opinion, are not enough. So those are questions how to better use get the best from the server in general. And this affects also aspects like the power consumption, also running the application fully on the CPU. What is then not only the event throughput, but the event per watts, and then what is the effect running on CPU. So all those kind of studies needs to be done. I know that have been done for the specific application, for instance, on the HLT, but it would be nice that we make possible for our community to execute them, again, independently from the specific field of experience of the expert in an experiment. So this is all the work that will keep us busy in the coming years. And this brings me to the conclusions that, okay, well, the talk was long, as was the preparation to migrate from HEPscore 6 to HEPscore. It was a multi-year process, but our hope is that now we have really made easier to then move to upgrade of this benchmark. So the concept will not change. We will add new workloads, and then we will somehow redefine the composition of the HEPscore in the future. But we have learned also how to make this transition smooth. Again, having done for HEPscore 23 already, the work of including ARM has been crucial. Because there are plenty of studies that have been made possible for that. So it was something important decided at the right moment. And I would like to thank all the experts that pushed a lot to get this done from all the experiments. So because 1 year ago, we were at that point of preparing those workloads. What else? The database. The database is a place where we share results. So it's crucial that sites that are running the benchmark make this attempt to send the results to the database. So it's valid for multiple aspects, for long-term persistency of those data, sharing with the community, also giving to us the possibility to inspect what was running there. So consider to do this when the next time you will run HEPscore. And that's all on my side.
Great, thanks.
Sorry for the length.
So we had a fair amount of discussion through the talk, but we still have time, I think, for a little bit more. I see that Charles was the first with his hand up, so go ahead, Charles.
Thank you for a super interesting talk. So I've got a couple of questions. The first is, when the score is reported to the database, is it just the overall score, or is it broken down into the different workflows? And the reason that I ask this is that it would be really interesting to track over time, especially as new architectures emerge, if some architectures and some combinations of memory speed and amount of memory and disk and things like that make some workflows really prefer one configuration as opposed to the other.
The answer is we have everything. So details at the level of each workload, even each copy of the workload running. So yes, all those studies can be done. Again, I said there is material for a number of student theses if you want.
And the other question I have, maybe it's a little bit premature for this, is about integrating GPUs into the HEPspec. And what are your plans for different architectures in the sense of, Intel versus AMD versus NVIDIA? How are you going to manage optimizations for the different architectures? Because you can't just take the same code and compile it with different, even if you have some compatibility there, you can't just compile it for the various backends. If you really want to try to, optimize to the bare metal, because a lot of work actually has to be done to, say, optimize something for AMD versus NVIDIA because of the difference in the hardware.
Yeah, so typically we don't compile. So what we do is that we access CVMFS in a dry run. So this means that, yes, we need the hardware available. And then what happens, for instance, for CMS HLT is that it discovers what where it's running and then access the library that it needs. So this is the way we implement it. Clearly, this implies that we need the hardware to then prepare the workloads. We could do another approach and then enforce it, but then we have to cover the aspect that you say. So that we don't want to optimize it. We want to follow the recipe from the experiment.
All right, so it's going to be really up to the experiments to provide the binaries or whatever, yes, which are optimized or are made for a specific hardware backend.
Yes.
No, okay. But I even expect that you would not like to have Atlas provide you with a different image for NVIDIA, a different image for AMD, and again, a different image for Intel, right? Since for CMS, from what I understand, we just have a single setup, and it's up to the software to decide what it does.
Yeah, but essentially, so first of all, they have to compile their software, right? So if they have different binaries for the different GPU models, then we need them. Okay, this we need. So like for ARM, so we need is a different library set for ARM with respect to x86. It's not the same. So we need it. But how it has been compiled, so all the flags, the compiler flags, this is in the hands of the experiment and the expert help. We want to reproduce what will run in production. And only the experiments can tell us.
Okay, I now have a forest of hands, so I would ask people to be brief, both in their questions and in their answers. But next up is Liz.
Hi, yeah. If on 44 you listed like places, people who have given you GPU workflows, and I was wondering about Alice. I mean, isn't most of their work done with GPU these days?
You said Alice?
Yeah.
Yeah. It's one of the ones that will appear. So I mentioned that the ones that we already have.
I see. Okay.
And we will add the Alice one. Yeah.
Very soon. Okay. And I guess you mentioned something really quick about utilization of GPUs, but I don't think anybody really expects high utilization numbers out of GPUs. Isn't that right? I mean, they're accelerators, right? So if you max out the CPU, then the right metric is throughput, which you already use, right?
Yes or not, in the sense that one could say, okay, let's go as fast as possible, but then now we have other dimensions like the cost, even the carbon footprint that is also embedded in the amount of hardware that you put there, the construction of that hardware, right? Plus the energy consumption. So at some point, I believe that we will arrive at a point in which we will say, okay, but my GPU was half of the time idle. Can we profit of this other half that was idle to do something else? So I believe that even if we have to start with the event throughput as a starting point, that is just the starting point. So reason why I said that we have multiple dimensions now. So this is at least my feeling. Then this probably will need a dedicated seminar for that.
Complicated dimension is included. Okay, so next question from Andrea.
Hi, Domenico. What is the timeline for updating HEPscore this year to add the GPU workflows? I'm asking because I'd be very happy to give you the new ones we are developing right now that then should be able to run also on AMD GPUs.
Okay, so to get a new prototype that runs on GPUs of HEPscore, so we can prepare it multiple times in the sense that this will not replace HEPscore 23. To replace HEPscore 23, we really need that the GPU start to be used in production. So because HEPscore 23 is connected to the pledging and accounting process, okay? So to go through a modification of HEPscore 23 as this currency approach will require, in any case, I would say, a motivated step. On the contrary, having a prototype that runs also on GPU, this we can do anytime. So we could start with the three that we have. In any case, we have to consolidate HEPscore as it is. So we somehow put on hold the activity on GPUs. This gives to you and the others the possibility to update their software. So I know that MedGraph is a couple of years old, probably the version. The MLPF also. You are telling me that now the CMS1 has a new version. So feel free to contact us and give to us the new version when you have. We can update it multiple times.
Oh, okay, great. Thank you very much.
Thanks. Okay, Stefan's next.
I wonder how you want to solve or tackle this problem that you have different kinds of GPU uses, right? So you could have an application where you basically from one CPU core enqueue some work in the GPU and max out the device. There could be another application which actually is CPU bound and doesn't manage to push enough work in the GPU so that doesn't really profit from having a weak CPU. You will always have this problem that you don't really know which type the application is and how this ties then to the final HEPscore.
Yeah, so the answer is in the title of this slide. We are still learning, and
okay.
Frank, I would like to learn from you, from the community. So we don't have their pretty good concept on that. So I think that we need to mimic in the benchmark what is done in production, but production probably is still evolving the way to use. Or that's not. Well, I think in terms of a level trigger, there it exists.
Yeah, okay, so Marcus is next.
Yeah, so you have really studied in extreme detail how our workloads behave on a server in isolation. But when we look at how we use sites, we don't run workloads on a machine and not use any other component of a site. So to get an understanding of how efficiently and effectively a node works, or one needs to measure it embedded in a site, so that you also, because we have lots of workloads that are also I/O intensive, and if I use a super performant node, stick a very poor network into it, and connect through that to a very slow storage system, I will get no performance. So I'm not saying that we should give up on this benchmark. It's really useful and it gives us a lot of insights. But I think we should also start looking at how we can measure and compare the performance of standardized workloads on different sites, including the I/O.
Okay, so there are two aspects there. One is the ability to inject this in standard production setup, and this we have proven that we can. The other is what you mentioned, so being able to access the data that those workloads have to run through the storage. This, as of today, we don't have, in the sense that we have the file inside the image, but I would say it's quite trivial to extend this, saying, okay, it could access an external file or set of files. It's just work, but it's extremely simple. So it's in our reach if we have the time and the person power to do that.
Useful.
Yeah, I agree.
Okay, thanks.
So let's have probably a last comment from Andrea.
So it's actually a reply to bouncing on something that Andrea said about the AMD GPUs. My impression is that also we actually need the AMD GPUs with CIs and all the rest. And so maybe I don't know. Can I ask Andrea if you have an AMD GPU node here at CERN to use for a CI? Give it to us. No, but maybe Domenico wants to comment on this. And same thing.
We don't.
So as far as I know, yeah, we lack of AMD GPUs. So those are extremely rare, even through those cloud resources that we could access. So they are not available. So NVIDIA dominates that. So
we may have some soon.
You may have. Okay, good.
The ones that are currently around, yeah, we don't get feedback. We're happy to at least have those one or two ourselves.
I have another question. Thanks a lot for the talk. Very, very interesting. Your seminar reminded me of something that we tried to deploy in the 2010s or 12s, which was called machine shop features, where the idea was that you land on a computing cluster, but then every worker node not every worker node, but worker nodes are different models, and landing on a worker node, you would like to know what power does this worker node provide to me, and then the experiments could use this information in order to, for a simulation job, for example, say with this power I can produce not n events, but two n events, whatever. Is there any idea of all the information that you're collecting, making them available to the...
Yeah, that could be used, but again, this plot shows that what we will store as machine job feature will be probably or the lowest value, that is the measurement with hyperthreading enabled saturating the whole machine, or the top measurement that is the other. So are those two extreme cases, no? But indeed, in reality, when the job will run, it will perceive a different performance that ranges between those two. So yeah, it depends on how this can be used. So I can imagine also your second question. So that the best would be to probe what is the status at the time of the pilot, more or less. So there are experiments that are doing this with the very fast benchmarks. Exactly. It's not bad as an idea. One of the fastest benchmarks that we have could be used, or whoever is still using something based on Python could still continue to use it. So I mean, I don't see this as a problem. But makes more sense. Yeah, in my opinion, makes more sense that just relying on one or two static values.
Very good. Okay, I think we finally exhausted the questions. So our thanks again to Domenico for a super interesting talk and lots of interesting discussion as well. So let's close the meeting here, and we look forward to seeing you in March, when we'll be hearing from the vendors about their plans and hopefully their software plans as well. We'll make sure we pass that message along to them. So thanks everyone very much for joining.